going over 1.4, continuity and one-sided limits. Alright, so the definition of continuity is when your function has no holes, no gaps, no breaks, or jumps. Okay, so if I have a function and I have a C, my function is continuous at C if and only if it has no holes, no gaps, no breaks or jumps. Okay, I'm going to go over three situations in which a function is not continuous. And a function is not continuous. The first of which is when I have a removable discontinuity. So if I have a function that looks like this, there's a hole at C, so I say that f of C is not defined. Why? Because I have a hole at C. So there is a hole. Alright, the second situation number 2, is when the limit does not exist. So when does the limit not exist? Usually when we have a break at C. So if the limit of f of x as x approaches C does not exist, then my function is not continuous. And the last situation is number 3, when we have a function that has a hole and it is redefined somewhere else. So this is when the limit of f of x as x approaches C does not equal the point at C. And usually when we have this, we have a removable discontinuity. And in situation number 2, when it's not continuous, you have what's called a non-removable discontinuity. And then, so that's it for that. Now here's the definition of continuity when we have definition of continuity. So the first thing, that the requirement that it must meet is that f of C is defined. So in order for a function to be continuous, f of C must be defined. The second condition it must meet is that the limit of f of x as x approaches C must exist. You have to be able to find a limit if it is continuous, if that function is continuous. And last but not least, the limit of f of x as x approaches C is equal to that point, right? So I have a function, here's C, right here, the limit exists, there's no breaks, there's no asymptotes. F of C is defined, this is f of C right here, right? And then f of C equals to the limit, so we're good. Alright, let's see. We're also going to, well, let's look at some examples. Example 1. I have the function f of x equals 1 over x. Let's discuss the continuity. So what about the continuity of this guy? Well, I know this has an asymptote, a vertical asymptote at x equals 0. So this has a what's called a non-removable discontinuity at x equals 0. Okay, let's take a look at another example, number 34 from the homework assignment. So f of x equals 1 over x squared plus 1. Okay, well this one, let's see, I know it has no holes and no asymptotes because x squared plus 1, if I set that equal to 0, I don't get any real solution, so I say that this one is continuous. Oops, continuous for all real numbers. And then let's take a look at another one. Let's see, number 46. And I have a piecewise function where I have negative 2x plus 3 for x is less than 1. And I have x squared for when x is greater than or equal to 1. Okay, now I know that for a piecewise function, one of two things can happen. I can have a function that breaks, so I have a piece and another piece going the other way, or I can have a function that connects in a smooth curve. So in order for me to know what situation is happening, I'm going to have to plug in 1 into both of these equations. If the situation is this first one right here, then both of these equations are going to give me something different. They're going to be equal to something different. However, if it is continuous and they meet at the same point, then they're going to give me the same answer. So let's plug it in. In the first equation, negative 2 times 1 plus 3 equals 1. And then if I plug it into the other one, 1 squared equals 1. And lo and behold, they are the same, therefore they meet at the same spot right here. Like here's 1. They meet at the same spot, so this is continuous for all real numbers. And usually that break will happen wherever that number is. Right there, whatever that number is. Alright, so let's take a look at another one. Another example, this is number 36. I have f of x is equal to the cosine of pi over 2x. And I know that the graph of cosine looks something like this. And then that's just a number multiplying x, so this is also continuous everywhere for all x. So basically you want to try to relate continuity with the domain of a function. So the domain usually tells us or gives us a hint about its continuity. Alright, and then if we explore the difference between removable and non-removable discontinuity algebraically, that's when you can, if I have, for example, like number 42, if I have f of x equals x minus 1 over x squared plus x minus 2, so I'm going to factor that and I get x minus 1 over x minus 1 times x plus 2. Okay, the fact that these two factors are going to cancel out, that means I have a removable discontinuity. Whatever is left over, in this case the x plus 2 factor, so now I have 1 over x plus 2, that didn't go away, so I know that this becomes a vertical asymptote. And so that's a non-removable discontinuity. So I have a removable discontinuity at x equals 1, and I have a non-removable discontinuity at x is equal to negative 2. Okay? And let's see. So now that I know something about continuity, now I'm going to use one-sided limits to show that something is continuous, to help me show that something is continuous. But first, let's do the one-handed limit. So usually, or one-sided limit. So if I'm coming from the right side, you will see something like this. The notation is a little bit different. So limit of f of x is equal to x, f of x as x approaches c from the right. So that means if I have a function and it looks like this, whatever, c's right here, from the right means I'm approaching it from this side. So I start here and I'll travel until I get to that c, and that'll tell me what the limit is. And then a left-handed limit from the left side, you'll see the notation like this: the limit of f of x as x approaches c from the left with the little minus sign. That means I'm approaching it this way from the left. So coming from the left, travel along the line until I get to c there again. Alright, that's the whole one-sided limit thing. So like I said, one-sided limit allows us to define continuity. So the definition of continuity is such that, let's see, on a closed interval, it says that the limit of f of x, or my closed interval, a, on my closed interval a to b, it says that the limit of f of x as x approaches a from the right is equal to f of a, and the limit of f of x as x approaches b from the left is equal to f of b. So if I were to have something like the limit of the square root of 1 minus x squared as x approaches 1 from the, as x approaches negative 1, I'm going to prove that it is continuous using left-hand limits and right-hand limits. So what I do is, first I take the limit as the square root, or of the square root of 1 minus x squared as x approaches negative 1 from the right, plug it in there, I see that it's 0. And in this case, my graph looks like this: 1, 1, negative 1, and 1. So it looks like a circle like this, and this is b, and this is a over here. So if I were to plug in negative 1, I see that it is in fact f of a. So if I plug in negative 1, I get 0. My limit as it approaches negative 1 from the right, remember from the right is coming this way. So from the right, travel along right here, it is also equal to 0. So this is equal to f of a. Okay? Now I want to check the other side. So the limit as the square root of 1 minus x squared approaches x, as x approaches 1 from the left, so coming from the left, travel from the left over here, so it should equal 0, and if I plug in 1, I get limit of 1 minus 1, okay, so that's also equal to 0, so that is f of b. So I can say, therefore, remember the 3 little dots mean therefore, f of x is continuous on the interval from negative 1 to 1. Usually you're given the interval. I should have put over here, at this point right here, that on the interval negative 1 to 1. Sorry. Alright. And